Before we start, a little recap on mapping. We introduced two different map types. The first is the grid map and the other is the topological map. Both have very different applications. The topological map is the one you would use in Google Maps, where you have a list of points of interest, including street intersections, as well as edges that connect between them, and that creates a graph. The grid map is a pixel-based map that you would use in the local vicinity of a robot. For example, you have a vacuum cleaning robot in your living room, or you have an autonomous car that has been navigating through a city using a topological map. It will then need to create a grid map, or in that case a voxel map in 3D of its environment to plan locally where it can drive. We talked about how to discretize the map values from world coordinates into discrete map coordinates, and we talked about more efficient ways to store grids in what we call KD trees, and in particular the quad tree, that is the 4D tree, where pixels are stored in quadrants, and then once the quadrants exceed a certain number of elements, they are subdivided into 4 smaller quadrants and so on. The advantage of the quad tree is not only that it has log n memory and retrieval speed capabilities versus the grid map, which requires order of n steps to store or read, but you can also store real valued data in the quad tree. So instead of saying this is everything here is left of pixel 150, I can say everything here is left of 0.5 meters or below 0.5 meters from this coordinate. All grids are graphs, but not all graphs are grids. This is important because we will use graphs for planning, not grids. And when you store stuff in an octree, you will usually treat it as a grid and then create a graph structure from it in order to do your planning. Finally, I want to reiterate why we need mapping. The first reason is for navigation. I want to go and find routes from A to B. And the second is for localization. I want to recognize some kind of landmark, and I can search my tree on where this landmark is, and then I know where I am. Now, I want to say this because today we talk about ways to make maps more accurate and more suitable for navigation. And for that, we introduce probabilistic mapping and the notion of configuration space. So the first problem with the map is localization. Here I have been running the map using just the robot odometry. You see it started driving straight up, and then when it did its right turn, I misjudged the angle by a few degrees, which led to a tremendous error in my mapping performance. I have this wall here all over the place, and it keeps shifting as the robot starts increasing its error. Now it gets worse and worse, and the map gets completely useless. Now, even if I remove this by using GPS and compass, I still have laser uncertainty, which comes from two sources. The first is the objects might reflect poorly sometimes, but the second is the robot actually does wobble. If it moves up and down, so the laser beam becomes longer and shorter for the same obstacle. But even worse, in this case, the laser might hit the floor, and when that happens, like when you brake, the robot juggles, or you turn, and you would actually sweep over the entire floor, and you think that this entire space here, for example, is not navigable anymore. So how can we deal with this? When you think about it a little, the idea would be you have to see something multiple times for it to be really an obstacle, and we can do this by just counting the incidences of an obstacle happening at a certain grid cell and derive some notion of probability from that. In that case, each entry is now the probability of a cell being occupied rather than a true-false value. And in this case, the probability higher leads to darker values. And so you see the obstacle here is probably centered around the dark part here, but the robot is not so sure whether it's not even there already. So how do we do this? A very, very basic approach is to just say the probability of an obstacle is 0 in the beginning, and whenever a laser hits, I add 0.01%, 0.01 to it, that is 1%, and as the map increases, I at some point say, okay, I have 1, I stop filling this bin up. But I can also say, whenever I don't see anything, I reduce the value by 0.01, so then obstacles will eventually disappear, and only obstacles that really happen to show up a lot are true obstacles. I can also use thresholding then to say, okay, I've seen this more than 80 times, so this, or 80%, so this is now an obstacle that I set to be true. Now I've done this using Weebots. I collected this map using raw data, and now I did the same using the technique of incrementing, and what you will see is all the spurious measurements here are gone, and I remain with very bright obstacles that I saw very often, and less brighter ones as the robot hasn't seen these things more than, let's say, 50 times. I can then use this data and threshold it and say, okay, these are the obstacles that I will store on my map. And you see here, in this case, even this part of the circle has only been stored as 3 points because it hasn't been bright enough. So if something like this happens, maybe you want to change your threshold to be 90%. And as you can already see, this will involve a lot of fine-tuning versus being a principled method. For this course, this is all you will get. There will be other courses in this specialization where we explicitly deal with probabilities and build this up from first principles. Now the goal is really just to create a map representation that we can use for studying other algorithms like path planning. Now, how can we use this for navigation? Now I have created this obstacle map, and I asked the question, what's the shortest path for the red robot to go to the white goal? And you might think that it might be this path through these obstacles here. But then, of course, you might think, well, maybe the robot wouldn't fit through that. And there's only one way to actually move the robot there and see if it fits and check for collisions. But there's actually an easier way to do this, which is to simply grow all the obstacles by the radius of the robot and turn the robot to a point. This is called the configuration space because the robot now is represented by a point x and y. So this is the x-axis, this is the y-axis. And I can say that the configuration space, wherever it is black, the robot cannot be, and wherever it is white, it can navigate. And in this case, I didn't fully color this, but I hope you get the idea. I can now just navigate between these two obstacles on this very narrow pathway here. But when I do this, I know that my robot will not hit the obstacles. Now you can see this is computationally quite expensive. I did this in Inkscape and swept the robot around this ellipsoid here to see how this would look like. Easy, more difficult to do this for a star shape. As you can see here, when you sweep it, points in the map space become curves in the configuration space. So this is a little tricky to do completely and fully using a computational method. So instead I propose to use something simpler, which is a simple blurring operation. And what I've done here is I took the map input that you see here and I blurred it so that all of the obstacles grow and eventually touch each other. And now I know that depending on how much I blur this, the size of the blurring operation can be a function of the robot disk size, and I can do that until I get a configuration space in which this passageway here is illegal, and I can know that everything I now navigate will be completely safe. So in order to do this, I added a threshold operation here as well, and now I can see that the only path or the only paths from red to white are via the actual line following course that I have been using earlier. All right, so this can also be done in 3D. Imagine the robot is not a rectangle, not a disk, but a rectangle. Then the robot wouldn't be able to, it would be able to go to this narrow space here, but then unless it turns, it wouldn't fit through this passage on the top here. So I have now grown my obstacles more in one direction and less in the other. And so you see all of the remaining space is something I can safely place my robot, but then I cannot move it through that narrow passageway because it will get stuck here. And again, the robot, I drew the rectangle so you can see it, but the robot is just a point, and I took a note here that this is the orientation of 0 degrees. Now I can do the same thing when the robot is rotated. So I grow the, I flip the order in which I grow my obstacles, and now you can very easily move the robot from left to right, but you can't go through the narrow passage here. Now I can create a representation where I stack these different angles. So I did this for 4 different values. They are of course the same, so 90 and 360 is the same as 0 and 180. And I can now think about this as moving from one plane to the other as soon as the robot turns. Now, if I want to find the shortest path from here to there, I can move till here, then I can jump over to this other plane. That means the robot has to be turning by 90 degrees, and then I can move through the top narrow corridor, and then I can arrive at my goal that way. So the important step here is we forgot about maps, which are just display relevant information, and talked about ways to make the maps actually useful to navigate on them. How to navigate is a different story. We will talk about this later, but I want to conclude the mapping team by pointing out to you that the actual map is a map that is useful for navigation, and if I have to do a lot of collision checking, this is much less useful than storing a data structure that I can use directly as a topological map graph and feed to a planning algorithm. And so in this case, if in case you don't see, I can turn this grid into a topological map, and I can do that for this grid. So I have 4 topological maps, so 4 planar graphs that are lying on my table, and then I can simply connect all of the nodes which are reachable, or where the robot can turn by vertical connections. So whenever I'm on a node and the robot can turn and actually would still fit there, I have a connection up or down, and in areas like this one where the robot cannot turn anymore, I simply don't have a connection to the lower layer. How to do this is using an operation called a convolution. This is also how blurring on computer graphics is implemented, and you will see that explaining it via graphics is much simpler than using the raw signal processing, which I just do real quick here. The key idea is that the convolution is between 2 functions. In this case, one function is the blue rectangle, the other function is the red rectangle. And what happens is I move one of the rectangles against the other one, and I compute the product of the 2 at this position. And I don't only compute the product at this position, but I actually add up the product of the 2 functions at all positions, and the result of this operation is the outcome of the convolution at this point. Now this sounds very complicated, but watch this animation. As the 2 functions approach, the product and the sum of the products increases. The sum of all the products is maximal when they overlap completely, and then as the function leaves the other one, that sum of the products goes down. Now this is even more complicated in 2D, where this equation looks like this, but actually much simpler to visualize. In this case, I have one function here, which is an image. here 28 by 28 pixels, and the other function is a small kernel of 3 by 3 pixels. And what happens here, the outcome at a certain position is the weighted sum of all of the pixels multiplied with each other and then added up. And so what I do is I multiply each pixel value in the kernel with the underlying pixel value of the image. I add them up and I put the result into this cell, and then I move the kernel to the right. This is exactly what this operation does. I have the two sums here which are sweeping from minus infinity to plus infinity, or in this case from 0 to 28, and the other ones will sweep from -1 to +1. So I go along this entire kernel, and now I multiply the values here together, and this is the result of my convolution operation. Now, concrete example, here I have what is called a Gaussian kernel, which takes the neighboring values and adds them in to, and then normalizes by 10, which then normalizes this whole operation so things don't become brighter or darker, but they essentially average the pixel values around a pixel value. And when you do this, something very noisy becomes a little blurry. So this is usually the first thing you do in any image processing pipeline, but this is also exactly the operation that we use to grow our obstacles. And in order to grow those, we can change the kernel size. We can use a 4 by 4 kernel or a 5 by 5 kernel, or we can use a 10 by 30 kernel in order to grow objects vertically more than to the right. And then once we turn the robot, we can use a 30 by 10 kernel, but we can also have kernels where the robot is kind of diagonally in it, and we have zeros and ones where the robot is. Now that we did this, there is one very interesting convolution operation, which is edge detection, which uses the so-called Sobel kernels, and those have zeros here in the middle and minus to the left and plus to the right for vertical edges, and the same for horizontal edges just turned by 90 degrees. Now, how does this work? If you have an image which has no edges whatsoever, you would take stuff from the left and subtract it from stuff to the right. Now both readings are the same because the image is smooth, so the result is 0 and you don't see anything. If the pixel values vary dramatically, however, you get a very high value, and therefore whenever you have an edge in the image where intensity changes abruptly, you will get a high output from your convolution. Here I've done this by applying first the vertical and then the horizontal Sobel operator, and I turned this very noisy image here into a very clean representation of all the edges. Obviously you can also do this on laser data and detect edges in laser images, so there are very many use cases for convolutions, not to mention convolutional neural networks, where those kind of kernels are actually learned to find images, and a dog might be some random combination of learned kernels and spatial relationships thereof. Now, to show you that this is really just a blurring operation, I took the image here from my PowerPoint slide, and I applied the PowerPoint blur filter with the highest radius possible, and you get something like this, where you can see that the objects actually do grow. And once I apply a threshold operation to this, I would be able to blur them so much that this becomes unnavigable, or in this case actually the robot would go very closely in the middle between the two and safely keep away from the obstacles, much like we have done when we computed the configuration space manually. All right, so there's one more thing for this module. So far, we have only used the final point where the laser hits an obstacle and said, well, this is a grid cell that we can update now and increase its probability to be an obstacle. When we fire the laser, we learn a lot more, however. We know that all of the grid cells that it has passed are actually empty. Otherwise, it wouldn't go to reach the obstacle. So what we now can do is, instead of just updating the pixel where the laser hit, we can also update all the pixels that come before it. And in order to do this, you can use Bresenham's line algorithm. It's an algorithm from 1961, now built into every graphic card in hardware. It's very fast. It only uses integer operations. And you can see it here. It draws a line from x0, y0 to x1, y1. And what you can do is you can compute the slope of this line, which is y1 minus y0. This goes increments positively downwards and rightwards. So here the slope is 4/10. And now I have a line equation where I can compute the y value by sweeping from x0 to x1. Now, what makes Bresenham's algorithm a little tricky is that you have to check which quadrant you have. So whether your for loop goes from x0 to x1 or from x1 to x0 and so on. This makes the implementation a little complicated, but in practice, you will be able to just use any line drawing algorithm that comes with some kind of graphic library and essentially draw a black line onto your Weber's display for every laser scan that has been successfully passing this area. Now, in summary, I hope you saw maps are noisy due to localization. Nothing we can do about right now instead of using GPS and compass, and sensor errors, and that makes them completely useless. So we need techniques to make clean representations so that we don't run into obstacles that don't exist or are blocked by them, even though they're not there. But we also need representations that facilitate planning and actually abstract this obstacle collision problem away. For that, we introduced the notion of configuration space. This is very easy for a circular robot, which directly turns into a point, and it becomes a 3D configuration space as soon as the robot is not a circle anymore, but like a car, a rectangle, and where it matters at which orientation you want to place it into the map. We introduced the operation of using a convolution for doing this in a very simple manner, very worry-free, very simple computation, but it requires some fine-tuning on the kernel size. It's something you have to play with in practice, and this is something you're going to do later in this module. Finally, lasers are not just measuring points where they hit, but they are also measuring where they don't hit. So something to consider when you want to create a clean map representation. Whenever your laser passes some area, you can clean up that area of your map and assume that it is free for the robot to move.